So Maria and Liang, do all the speakers know this link and passcode?
They yes, they should have had the link and the code, but I'm now trying to see if there are like, for example,
Yeah, I managed to find everything, but it's a little bit complicated. In my group, so we usually send email to everybody before the meeting, but probably
okay, yeah,
it's not.
I'll do that right now. So for people that didn't find the link, I can try to send it right now. Yesterday there was no problem. All people.
Yeah, okay. And then should be okay. Should be okay.
Yeah, but I think yesterday actually for the people that I didn't see in the before 6:30 I sent some link. So I think I can just. So who is missing now? I think Lorenzo and so.
Lorenzo is the second speaker. Xiangyu is fourth speaker. Asaf is the fifth speaker.
Yeah, so I think Asaf, I'm adding him and.
I see.
So Professor Wang is here, yes, and Professor So Yongfeng Wang is here. Professor Xianghu Wang is here.
Professor, we're missing Professor Xiangyu Wang.
Yeah, he's not here.
Okay. I will send a message to him. Okay.
Okay. So and then okay. So let me see.
Xiangru Wang, his office is
okay
on the same floor with me. I can go to have a look.
Okay. So Uzne is here. Dr. Mukesh Kumar is here, and
okay. Just Xiangyu Wang asked me to send the link to him. Okay, I will send the link to him now. Okay.
Okay.
Hi, Maria.
Hi.
How are you?
Nice to meet you, finally. After we exchanged so many emails, right?
Yeah, that's right.
I'm looking forward to your presentation today.
Yeah. It's.
Do we have some news from the journal or not yet?
No, actually, so we need to send
some reminder, yes, because I think a month has been passed. Yes.
Yes, exactly. So it's like how it is going and so on.
Hello.
Yes.
Progress. How are you, Gucci?
Hi, Liang.
Hi.
Hi, Bruce. It's nice to see you here.
Nice to see you.
Thanks. How are you, Isna?
Sorry?
How are you, Isna?
Good, yeah, good. Everything is going fine, yeah.
In Israel still?
Sorry?
Still in Israel?
Yes, I am. So here is everything is better than the other countries.
I can imagine.
So it's luck to be here.
Okay, I think there was another speaker that may want to try the presentation. Usna, did you try the presentation yet, or would you like to try? Would you like to try quickly? Still, yeah, we still have 3 minutes, so you can try, please. Yes. So just to make sure that nothing will be wrong later on.
Xiangru, you can test sharing your screen.
Oh, okay. I'll try to do that. Okay.
Okay. So do you have animation, Usna, or?
Just a minute.
Can you see my screen?
Yes, we can see the screen.
Okay,
yes.
then I can.
So
I
want to say that because it's late in my time, I probably will miss your talk.
Okay.
But I will definitely come back to listen to your talk, because I know you already done very detailed job. I just want to come back to see all the plots you have. You probably present a lot more plots, right?
Yes.
Yeah.
Yes, some of them.
So the one
actually,
you showed us is just one example figure.
Yeah, actually, for the result, we don't. I don't present more plots, but just the way that how we arrived at that point. I think I will explain to the in the presentation. But we will, of course, I will submit them. I mean, I will exchange the manuscript with you as soon as possible.
Sure.
After this presentation, I will concentrate more. Yeah.
Sure.
Okay, so I think there was another speaker that thank you that could
shall
try the
we
presentation.
Yeah. Okay.
Yes, please.
Okay.
Could you try? We still have 1 minute.
Share my screen, right?
Yes, please share your screen.
I do this just a minute. Okay. Yes. So could you see my?
Yes.
Okay.
Okay.
Yes.
Okay.
Good.
Okay, that's good. Thank you. So I stop. Just. Sorry. Yeah.
Okay.
Okay.
Okay, I think Lorenzo is still missing.
And Asaf.
Okay.
Asaf.
Well, but Asaf is later, so I also sent both the link. So I think maybe he's joining later. So okay, so let's at this point it's 1:36:30, so let's start our session. So I just want to say a couple of words for introduction, and then I'll let Li Liang chair this session. So welcome all in this second day of the GRB session related to observational correlations, the theoretical implication, and the observational challenges. This is a series of three sessions. We had the first session yesterday. This is the second, and then we will have a third session on Friday. We want to explore the observed correlations, what are the problematics related to selection biases, and what are the observational challenges that we are facing with the telescopes, what are the theoretical implications. So that's why you will see that the sessions are a combination of observational correlation and theoretical discussion. And we will also have talks that will speak about the several properties of the GRBs. So thank you so much, and I will give the lead to Li Liang for chairing this part of this session. Thanks.
Okay, thank you, Maria. Thank you for your introduction. Let us to starting our talk today. The first speaker is Professor Bin Zhang. He will give a video talk on gamma correlation and physics implication. Welcome.
Okay.
Ready?
Yeah. Let me. Sorry. Let me quickly turn off something, just in case. Okay. All right. Can you see the?
Yes.
Okay. Thank you so much, Maria and Liang, for the invitation for me to talk about this GRB correlation physical implications at this session. I have been thinking about these things for many years, but just didn't have a chance to put everything together. So you gave me a chance to really put all my thoughts together in one talk. So there are many empirical correlations in the GRB field. This is chapter 2.6 of my book. I try to list most of them. I don't know whether there are new ones. And turns out that Maria, our chair, has her own book dedicated to GRB correlations. So the bottom line today, I'm going to talk about the correlations and physical implications. I will leave out the cosmography, which means that using GRB standard candles to measure cosmological parameters. But the bottom line is that GRB candles are not competitive compared to, for example, supernova because the messy physics involved. So I trying to sort out these correlations into two types. So the first type, they are related to the progenitor and central engine of the gamma ray bursts. So these include Frail, Denoty, Xu and Huang, Liang, Glenda, and I'll get through these relations later. These do not involve prompt emission parameters except the total energy. Energy is always there, but the second type of the correlations involve EP, for example, or other prompt emission parameters. So they are related to prompt emission mechanism. This is messier than the first one. So let's start with the correlations related to the progenitor and central engine. The first one, probably most influential one, is the Frail relation, which is related to the jet brake. So as we all know, from the light curve of the afterglow, one can measure the steepening when the jet opening angle is visible. When the gamma is decelerated enough, 1 over gamma cone is wider than the jet opening angle. And from this jet brake time, one can measure the opening angle. And then Frail back in 2001 noticed that the jet corrected energy is more or less a constant. This is from Bloom et al., which did got more bursts, and this is Berger et al. Not only gamma ray isotropic energy is more standardized, the afterglow energy is also more standardized. But if you really look into the data, so this means that E gamma iso is proportional to theta j minus 2. But if we really plot these things together, so you can see this is the theta and this is E iso, you can see is actually, this is minus 2 line, but there's a lot of scatter around this line. But this gives people a impression that the GRBs might have a standard energy reservoir. And furthermore, there were suggestions about the structured jet. The GRBs probably have, well, Rossi et al. Talking about the universal structured jet because the structured jet, the jet structure has theta minus 2, so exactly 1-on-1 matches, and to get something like this. And what Peter and I proposed is that probably we don't have to have exactly universal structured jet, which is not the case anyway. If it is universal, then all these dots should be exactly on the same line because there's a lot of scatter. So we can have a quasi-universal. So even if the theta, the power is not minus 2, it's minus 3 or something, as long as we have many of them, then the distribution, all the parameters has a certain distribution. We can probably reproduce this, even for Gaussian jets. So back then we said the Gaussian jets, for example, this one, and this one, they have certain distribution, but they probably can match up what the observations show. And it turns out that this structured jet general picture is confirmed not for long GRBs, but for short GRBs from 1708 to 17 because of the detection of gravitational waves. And it turns out that the Gaussian jet or some uniform plus cocoon jet fits the data the best. Okay, so that was the first, probably most influential relation, which is called Frail relation, which is related to the progenitor. Somehow the GRB progenitor tends to make either structured quasi-universal structured jet or standard energy reservoir. The next one is related to central engine, which is related to X-ray plateaus. So if we recall this canonical X-ray light curve, there's a shallow decay phase, which has a index say could be 0, could be up to -0.5 or even steeper. But Willingale et al. Proposed a empirical formula. This is not physical. So this function looks like the following. It's actually a plateau, and then there's a turnover, and here is the T break. And with this, he managed to fit some of the bursts very nicely. So 2 components, this is prompt emission component and afterglow component, but some of them are not that well. For this one, so you can see we need flares, and actually we need an additional turn. So this is the Willingale function, but there's a shallow decay and jet break. But nonetheless, Maria likes this formula very much, and she managed to use this fitting. I think she can confirm it later. I think probably when people use broken power law, shallow decay, use the luminosity and time break here, probably won't get similar results. But Maria showed that.
Yes, I confirmed that there are papers, Mangan et al. 2012, that have done that and they've shown this.
Okay, great. But with this formula, one can also get the extra luminosity at the end of the plateau and the break time. It turns out that there's a -1 correlation, even though you can see a lot of scatter. And another speaker today, Yongfeng Huang and his student Xuyan Huang in 2012 introduced a third parameter instead of just L and T. He introduced E and found an even tighter. This is a fundamental plane 3-dimensional correlation. And Maria recently did many fundamental relations, including instead of E, she used the L peak, prompt emission luminosity. And it looks like that the standard correlation becomes better when the third parameter is introduced. Then what is the physical origin of these Dynalty-Xu-Huang relations? The straightforward physical implication is the magnetar central engine. This is simply because there's a total rotation energy out there, which could be regarded as more or less the constant. And then the spin down luminosity and spin down time depends on the magnetic fields. Let's say the initial P is more or less the same among the GRBs. And it turns out that the luminosity is proportional 1/T. So this is very straightforward interpretation for a magnetar central engine. There are many papers discussing this, starting from Diane Liu 98, talking about not a magnetized, but a normally magnetized long-lived neutron star, which has an energy injection in much longer duration. But the general picture is similar. But the swift observations more and more show that magnetars are probably there, and the characteristic time scale for spin down is of the order of 1,000 seconds, which is make these guys magnetar engines. So I think these correlations are related to the central engine, and the magnetar spin down is the simplest interpretation. But Asaf and Hosni in the later session will propose some additional interpretations of these relations. Okay, and we move on to the third intrinsic correlation, well, engine and progenitor related relations, but these are related to Lorentz factors. So GRBs are highly relativistic jets, and there are several ways of measuring the Lorentz factor through opacity, gamma opacity, through deceleration, and afterglow and photosphere method proposed by Asaf. And there are in the literature different ways measure them and found the distribution of gamma. But recently with Yu Wang and Liang Li, we actually draw the attention. Basically, different methods are measuring slightly different Lorentz factors. We are talking about the Lorentz factor in different phases. For example, the photosphere Lorentz factor is during the coasting before the photosphere photons release, but the deceleration photosphere is here. Deceleration method is measuring Lorentz factor right here, and there could be a difference here through, say, other dissipation process, for example, internal shocks. So actually, one can measure these different Lorentz factors more precisely if one can measure both the deceleration feature and the photosphere feature for fireballs. Well, regardless, if we can measure Lorentz factors from a large sample of the GRBs, one can look into the correlations between gamma and something else, and it turns out these are the Liang-Galanda and the Liu relations. So these relations are talking about Lorentz factor proportional to the isotropic gamma energy to a certain power, or the isotropic luminosity of certain power. And it turns out that this index is around 1/4, 0.25 or 0.3, different papers. But I will get back to this later. So this is actually very important to understand the prompt emission mechanism in combination with Amati and Galanda relation, Amati and Unitoko relations. Okay, but the physical origin of such kind of correlation, energy, so basically more energetic ones have higher Lorentz factor. This is also related to the central engine. Actually, in the literature, there are two different ways of interpreting this. So from the magnetar scenario, one can reproduce this luminosity versus sigma, which eventually will convert it to gamma of the GRBs. And in in the black hole accretion torus scenario for long GRBs, one can also get something like this with two different mechanisms. So this is for a neutrino, anti-neutrino annihilation. The Lorentz factor can be calculated through the neutrino-driven wind. One can calculate the amount of baryon loading. And it turns out that the higher the luminosity, the more baryons you can take out, of course. However, relatively speaking, you get less. So the ratio becomes the ratio becomes energy between energy and mass loading becomes larger and larger. So basically, when you go to higher energy, you got a cleaner fireball. And for a Poynting flux dominated jet, especially for Blandford-Snaryak, one can do a similar exercise, but invoking different mechanisms. For example, the neutron capture. So for magnetized jets, protons cannot move. So in order to catch, cannot move across the field lines. In order to get more and more baryon loading, we need some neutrons to drift into the jet region and interact with positrons or collide with the protons and get more and more baryon loading. And it turns out that this also roughly produced this. So this is discussed in this paper led by Weihua Lei and us and Wei. So this is the bottom line of this. These two relations, they are related to the baryon loading process at the central engine. Okay, now we move on to more complicated stuff, the prompt emission mechanism. So these relations are related to the prompt emission parameters, for example, E-peak, spectral lag, variability, etc. Most famous one, of course, is the Amati relation and the Unitoko relation. So this time we are talking about E-peak, actually in the rest frame, corrected for 1 plus z, which is proportional to isotropic gamma ray energy or luminosity at a certain power A. This should be B, but in general, it's just 1/2. So it's E-peak proportional to E to the 1/2 or L to the 1/2. So these are the Amati and the Unitoko relations. And the question is, what's the physical reason? And it becomes much messier and more complicated. Before getting to the details, let's review that prompt emission mechanism is a mystery. So we don't know what, we don't know the jet composition, we don't know where, whether it is close to photosphere, internal shock, or some magnetic dissipation region close to deceleration radius. and how, whether it is produced through synchrotron radiation or thermal quantization. And for different, there are so many prompt emission models discussed in the literature, but one could actually understand this picture from this flow chart. So from the central engine, there are two ultimate energy sources. One is the gravitational energy, which is converted to thermal energy, the fireball. The other is the spin energy of the central object, either is from the magnetar or from the black hole. Then it will launch a Poynting flux dominated jet. And in principle, these two components could be there simultaneously, and depends on which one dominates. There are different energy flows. The thermal energy, this fireball is straightforward. So there's photosphere emission, there's a thermal acceleration making kinetic energy, and then kinetic dissipation, internal shocks make additional gamma rays to radiation. If you got the magnetic energy, Poynting flux energy, the Poynting flux can go in many different ways. If you can dissipate the Poynting flux below the photosphere, you can make a photosphere emission. Basically, Poynting flux can accelerate the ejected to kinetic energy, and then one can also have collision. If everything's essentially converted to kinetic energy, you can still have the internal shocks. If it is still magnetic dominated, the collision will make magnetic dissipation directly. So this is the ICRANet model we talked about. So the central engine can be quantified by these two parameters. Eta tells you how much thermal energy you have. Sigma naught, you quantify the other component. And then one can talk about all these kinds of energy flow evolution. So this is more complicated plots, but for different models, fireball model, dissipated photosphere model, initially magnetized internal shock model, magnetized dissipated photosphere model, ICRANet model, and hybrid model. Hybrid model means that everything is going out. So to me, the GRBs actually are diverse in terms of composition. Some GRBs clearly show the fireball signature. Some other GRBs clearly show Poynting flux dominated signature. Some of them probably in the middle show the hybrid property. So then we get back to this Amati-Unitoko relation and physical implications. Actually, this paper written with Peter was published in 2002. This was right after the Amati relation was discovered. And we discussed back then, actually the picture didn't change too much, what kind of prompt emission models we have and what kind of E-peak one predict actually. So internal model including internal shock and magnetic dissipation, and the pair photosphere. Innermost is the photosphere, and I also discussed the external shocks. But forget about these details, but the bottom line is the following. So if we really calculate E-peak, so we not only need the luminosity of the outflow, we also need the Lorentz factor of the outflow. So the bottom line is, back then, if we don't know this L and gamma relation, all the models can interpret Amati relation as long as you can introduce a correct L and gamma relation, because E-peak depends on both L and gamma. So as long as you find a correct gamma L relation, then you can interpret Amati relation. Okay, so that was back then. So then this is why this L gamma relation, which I discussed earlier by Liang, Galanda, and Liu, are so important, so essential to constrain these models. This comes to this Liang's 2015 model, which is not as famous as others, but to me it's very important to understand the physical properties, because if we put these three parameters together, one can find a fundamental plane relation. So L, ISO, E-peak, and the gamma. So this is expressions, but I just listed it here. So E-peak is proportional L to 0.55 and gamma minus 0.5. This is related to this. So this is the unitotal relation. This is the Louis relation, gamma proportional L to 1/4. If we plug in this one to here, this will give you so minus 0.12. So make it 4.3. So it's close to 1/2, but not quite. But this is very important. So all the successful models, prompt emission models, not only should interpret unitoku and Amati relation, they should also interpret these two. So this is what I'm trying to discuss in the next. So these are the three relations I just mentioned. And we know that photosphere model is actually, Dr. Ito has a nice paper published in Nature Communication. And he managed to show that the unitotal relation is well reproduced. I'm a little bit curious about the result because if really play this simple analytical model, if the photosphere shows up during the acceleration phase, then that is perfect because that in the photosphere model, E peak is related to temperature of the photosphere. So at the central engine, the temperature is actually proportional to L to 1/4. One can play with other things, but in general, it is positive correlation. So it's not surprising that one can get this unitotal relation if T0, the T photosphere is defined by T0. However, for a lot of the parameter space, the photosphere actually comes out during the coasting phase, which means that the fireball already experienced the adiabatic expansion. If we put this complication together, then E peak, which is proportional to photosphere temperature, it turns out that, so there's an additional factor here. It turns out that it's L to the -5/12 and gamma to the 8/3. So this is very different from this guy. So it feels badly in the saturated regime without the dissipation. So I don't know whether it was a dissipation, change of the conclusion, or maybe there's a coincidence between the gamma and some gamma L relationship make it reproduce this. So I'm looking forward to further discussion on this one. But I really hope to see that photosphere model can be developed to really interpret this fundamental plane correlation. So the correlation between the three parameters. And for synchrotron model is actually, if we write down E peak, this is the standard synchrotron model, and notice that the gamma times B prime is simply related to the luminosity of the outflow and divided by 4πr² 1/2. Then E peak is proportional L to 1/2 and R -1. So you can see synchrotron model is also very good. So the unitotal relation is right there. E peak is proportional L to the 1/2. Actually, it depends on R. So this is the key part. If R is the same for all the GRBs, then there's no problem. The problem is R is not the same for all the GRBs because, for example, in the internal shock model, R depends on gamma. So the larger the gamma, actually, the larger the R, the smaller the E peak. So this actually is opposite to these relations because when you have a larger gamma, then you have a smaller L. So you peak actually goes smaller, which means when L is larger, gamma is larger, L is larger, E peak is smaller. So that is not very good. Actually, Robert Mochkovich and Lara Nawak, they did detailed simulations. And they found that indeed, if you don't place any constraints and these correlations are not, they're distributing much wider parameter space, but with certain requirements or some some say fine-tuned conditions, then the Almaty relation can be reproduced. I want to say that the ICRANet model, the E-peak not only depends on R, also depends on sigma, and it turns out that sigma and R has a opposite dependence, because when you go to larger and larger R, sigma becomes smaller and smaller. So these two can actually compensate each other, cancel out each other. So in a sense, ICRANet model is better than the internal shock model to interpret the unit-Toku relation. Okay, let's move on to the Galanda and the Liangzhang relations. So this one is, instead of have E-peak correlated with isotropic gamma ray energy, but this time is the jet-corrected gamma ray energy. And Galanda 2004 claimed that this one has a tighter correlation than the Almaty relation. And the Liang and Zhang use a 3 parameter. This is the fundamental plane, but here T is essentially the jet break. So these two are intrinsically similar to each other. And they also found that it is quite tight. So the physical implication, this is quite mysterious. So from very beginning, I was trying to think very hard what is going on here. And I never found a very good explanation for this. Recently, Wang et al. Started to look into these correlations and found that they are less tighter than before, becomes comparable to, say, unit-Toku. So probably this is just dominated by the unit-Toku relation, which is a big relief for theorists. Finally, other correlations I don't have time to go into, but there's a L and spectral lag correlation. There's a variability luminosity correlation. They are very likely, I do have some interpretation, but I don't have time to get into it, but likely they are related to Lorentz factor and viewing geometry. So I will wrap up here, the summary slide here. Yeah, time is up. So I put all the correlations here and I just mentioned, but I want to emphasize that you can see there's a lot of dirty physics going on. So these GRB standard candles may not be very promising to do cosmography alone. This does not mean that we should not do it. We should use them and combine with the supernova and other correlations and eventually get interesting constraints. Thank you. I'll stop here and take questions.
Thank you. Thanks so much for this very nice talk. Any questions?
I have a comment actually on the, I know that you didn't have time to go through this luminosity tau lag relation, but I want to mention that a work of Sultana, Demos et al., they showed also that the extrapolation of this relation goes in the luminosity time correlation, so in the 2D dynasty relation. So if you could comment a little bit more on the explanation that you were thinking about, that it would be helpful. Thank you.
What relation I didn't fully get. So
in the summary, you were speaking about luminosity tau relation, lag relation. You said that you have some explanation you didn't have chance to discuss. So if you want to discuss now, I think.
Oh, you mean
nice.
the spectral lag?
Yes.
Oh, spectral lag. Okay. All right. Yeah. So I think it is clearly related to Lorentz factor because this standard time scale is R over C divided by gamma squared. So if your gamma is much larger, then the characteristic time scale is shorter, and that will be spectral lag can be translated to a larger Lorentz factor. And larger Lorentz factor, as we discussed, is related to a higher luminosity. That is theoretically and observationally proved. So I think that they're connected.
Okay, so thank you very much. And I have also another comment on cosmology that although I agree with you, being that the physics is not yet clear, but there are several possibilities and more connection between theory and observational properties can lead to find a standard set for cosmology. Actually, on your second slide, you were mentioning we are not yet at the point in which GRBs have the same precision of supernovae, but we were showing yesterday with Via Nilsson, one of my students, what it is the number of GRBs expected to obtain this similar precision. So we ended up saying that we needed to wait 1,150 GRBs.
Okay.
So we really need to increase the sample. But if we want to have like closed contours with cosmology, which with larger error bars, we just need 150 GRBs. So I just want to update the audience on that.
Thank you. I think Dr. Ito has a comment. I'd like to hear what he says.
Yeah, sorry. Yeah, thank you for the very nice talk. So yeah, I have just one quick kind of comment. So about the thank you for raising my work.
Yeah, so I just want to hear your thoughts about this one.
I completely agree with you that the gamma will give some key clues to the issue. But I think I didn't fully follow this formula, but I guess you're kind of using very simplified fireball model for driving this relation.
Right.
Yeah, but in the simulation, actually, there's massive. There is a massive dissipation due to shocks, and again, and also there's a mixing, which plays a role, quite important role in making the shaping the emissions. So you have to take into account all these. But I'd like to really check how our simulation.
But after all, it will change L and gamma in different viewing directions, and these equations should still play a role. So I would really hope that we can also check out from numerical and see whether this is correct or completely something is not understood.
Yes, thank you. Yeah, I'd like to check that. Yeah, thank you very much.
Okay, thank you.
Thank you.
Any more questions? Okay, if not, let's thank for the speaker again.
Thank you.
Thank you. Let's keep going to the next speaker, Professor Lorenzo Amati. He will talk cosmology through the epic ES correlation of the gamma ray burst. Welcome.
Okay, hello. Good morning or good afternoon. Thank you very much to Maria Giovanna and the organizers for inviting me, for giving to you a short overview of the EPIC-ISO correlation and specifically its possible as perspective user for cosmology. So, as you know, gamma ray bursts, of course, have very unique properties for cosmology, so they are actually of very much interest for different fields of cosmology. And here I just report two main flavors. So we are talking mostly about long gamma ray bursts, even though you know very well short gamma ray bursts are very important for multi-messenger astrophysics. But long gamma ray bursts are very important for cosmology. The so-called orthodox way of exploiting gamma ray bursts for cosmology is to use them for investigating their universe, thanks to their association with the explosive deaths of very massive stars. So they are very good traces of star formation, rate evolution up to the very universe. They help us to pinpoint the bulk of the population of primordial galaxies, which are invisible even to the most sensitive telescopes. And this is very well known, and several missions for the future are being studied specifically for this objective. But of course, today, instead, I will talk about the other possible use, very much interest of gamma ray bursts, long gamma ray bursts, that is exploiting these correlations for standardizing them in a way similar for instance, to type 1a supernovae, which are also non-standard candles by themselves, and they exploit a correlation, very well-known correlation, to be standardized. And this is to use them for investigating cosmological parameters and ultimately testing alternative cosmological model or dark energy evolution. I say this is still not completely accepted as an orthodox or a use of gamma ray burst that is commonly agreed. Nevertheless, there are several tens or even more than 100 articles in the literature on the main astrophysical journals actually demonstrating the possibility of using gamma ray burst for measuring cosmological parameters. So why, first of all, we should try to exploit the gamma ray burst also for measuring cosmological parameters? Well, very simply, very quickly, as you know, because of their different redshift distribution, because of the different methods, so luminosity distance, angular distance, or other methods. If you consider candles like type 1a supernovae or the baryonic acoustic oscillations, for instance, or even IGNs, or of course even the CMB, as you can see on the left, they show different sensitivities in the omega m, omega lambda plane, where of course you know very well omega m and omega lambda are the ratio between the actual density of matter, for instance, or dark energy with respect to the critical density, with all the probes pointing to actually a flat, so-called flat lambda CDM universe, where omega tot is more or less 1, whereas omega matter is around 0.3. And this provides us with the view of an accelerating universe, or in general, a cosmological constant. So in addition to this, so first of all, by combining several probes, you get more tight and more reliable constraints of the cosmological parameter, and also you get less dependent on the possible systematics. For instance, the type 1a supernovae themselves can be affected by several systematics, but that are listed here. I do not go into details, but the correlations that we use between the peak magnitude of the light curve of type 1a supernovae and the stretch of the light curve, of which the magnitude at a given time after the peak, which is called the Phillips relation, may be affected by several systematics effect. And this is an example. This is a quite old contour plot, again, omega m, omega lambda plane with Z-wave supernovae, CMB clusters, for instance. And if there is a systematic of only 0.1 magnitude in that correlation that is used to standardize type 1a supernovae, this kind of contours could move by such an extent in the omega m, omega lambda plane. So again, providing and investigating further cosmological probes is very, very important. But what we are aiming at the end, all these probes that I already mentioned, first of all, the CMB, but the type 1a supernovae, baryonic acoustic oscillations, and so on, large scale structure, and we are also now going to have the Euclid exploiting the galaxy distribution and so on. Why we should add again a further cosmological probe, what we are aiming at. Actually, this is the picture. We know very well most of the content of the universe is dark, is unknown. Dark matter is a very big standing problem since several decades. And now since the end of the 90s, we know again that the universe is accelerating, possibly under the pressure of this dark energy. This is a very simple classical way of stating the equation of state of dark energy. So the existence of this component in the universe that is providing acceleration is again confirmed by several probes, and also including of course the prediction by the inflationary model of the universe. However, what is unknown is the possible evolution. So you see in this equation, W0 is the actual value, the current value of the density of dark energy, whereas WA is the evolutionary term. But we may also want to explore further probes, specific gamma ray burst, to test alternative models. So if we take the Einstein equation, field equation of general relativity, of course, we may also not only change the right-hand side, which means working on cosmological constant and dark energy, but also the left-hand side, which is assuming the so-called F of R, for instance, gravity models. And as can be seen here, especially on the right, if you have a probe that extends the redshift distribution much beyond the type 1a supernovae or even baryonic acoustic oscillation, so up to a redshift of 8 or 9 or even more, like gamma ray burst, you can actually, despite there is evidence that the effect of dark energy comes into play at much lower redshift, so around 0.5, 0.6. Actually, if you want to determine the cosmological parameters, the evolution of dark energy in the Hubble diagram, which is like these two diagrams on the right, where you have the distance module or the luminosity distance as a function of redshift, you can see that you can discriminate between different models. These are different lines correspond to different models. In the top panel, in the bottom panel, you have the delta with respect to a given fiducial model as a function of different assumption of the equation of state of dark energy. So this means that you need a very extension to very high redshift if you want to be actually sensitive to the evolution of dark energy. So the most investigated tool for standardizing gamma ray burst, up to now there are also, of course, other lines of investigation, but for sure the most popular in the literature is the peak isocorrelation, or also the peak luminosity correlation. Again, I just recall that when we were talking about the unit of correlation, this is peak luminosity, not the average luminosity of the burst. So we know very well, and Bin has already given right now a beautiful overview of the spectral peak energy of gamma ray burst, and it's, how it is a key parameter for the emission physics of gamma ray burst. So I don't need to tell you that the typical new spectral gamma ray burst peak at a photon energy, which is called the spectral peak energy, and this peak energy can range from 10 keV to thousands of keV. And of course, if we know the redshift, since 1997, we know the redshift of gamma ray burst. Now we have almost 500 gamma ray bursts with measured redshift. And we know that radiated energy in the isotropic emission assumption, which is the most conservative one that we can do, given that we are still lacking a solid way to infer collimation angle of gamma ray burst, the radiated energy, of course, extends from over several orders of magnitude. We know very well, and this is what was found in 2002, so almost 20 years ago, on the first very small sample of Bepo-Sachs gamma ray burst with measured redshift and measured spectral peak energy. There was this evidence of correlation, even though the number of gamma ray bursts was limited, the correlation was already significant. And this was confirmed by several measurements in the following years by many other instruments, of course. And this is a subsample. Actually, this is not the complete actual sample, which includes even many more gamma ray bursts, but this is a subsample of more than 200 gamma ray bursts with measured redshift and measured spectral peak energy, considering standard long gamma ray bursts, where you see in blue the swift ones. So what are the main characteristics besides its high significance? The correlation, as you can see, this is a log-log plane, so we know it's as Bin Zhang also described, this is a Power relation with an index of about 0.5. And another main characteristic of the correlation is its dispersion. So this correlation, if you model the correlation with a simple power law or a simple linear regression in the log-log plane, you don't get a good, for instance, a good chi-square, because the correlation is more dispersed than what you would expect with respect to simple Poissonian fluctuations of the data around the best fit. So actually, the best way to model this correlation is using one of the likelihoods that have been proposed in the literature. We take into account also the so-called extra statistical scatter or intrinsic dispersion. So the model of the parameters, this is one of these likelihood, the one by Agostini, but most popular is also the one by Reichardt, and there are other similar likelihood methods that at the end apply to this correlation provide very similar results. You see that the other parameter is this logarithmic dispersion, which is around 0.2 for the peak EISO correlation. So an important fact is that, of course, there have been many debates on if this selection is and to what extent this correlation is affected by possible selection effects. So some authors expected that different detectors, which have very different sensitivities as a function of energy, for instance, would measure different correlation. However, as seen here, we show the correlation for BepO-SARS-CoV-2, SWIFT, and Fermi GBM, and also here we put all of them in the same plane. Gamma ray burst detected them with spectral parameter measured by different detectors follow the same correlation, which is showing that actually the sensitivity and energy band of the detectors is not so relevant. It's important, of course, but it's not does not play a main role in shaping the correlation. And as we know, as again was described in the previous talk, the same correlation holds if we, instead of the radiated energy, we use the peak luminosity. Yes, what does it mean this? If you have a look at this plot, we see that the radiated energy and the peak luminosity are very well correlated. So actually they are indicating the same things. They indicated the brightness of the GRB. So what is at work is a emission mechanism dominating for most GRBs in the most of the phase of the prompt emission, which relates the spectral peak energy to the brightness of the GRB and the brightness of the emission. Of course, each of the correlation using either the isotropic radiated energy or the peak luminosity has drawbacks. For instance, for the peak luminosity, of course, it depends on what you choose. What is the time interval on which you compute the peak? Of course, the peak is also reached at different wavelengths, so this creates an uncertainty. And also, of course, we have to keep in mind that we are correlating the peak energy, the spectral peak energy of the time average spectrum. So it is, of course, most consistent to correlate the spectral peak energy, the average spectral peak energy of the average spectrum, to the total radiated energy or average luminosity that is radiated in the total spectrum. So the idea here is that actually the peak, when you use instead the peak luminosity, you are using it as a proxy of the total radiated energy through this correlation. I cannot go into more details because I want to focus, of course, on the cosmological use, but this is also to show that, as is very well known also, if instead of a time average or time integrated analysis, we do a time resolved spectral analysis, like in this case, so you take the gamma ray burst, you divide it into several time intervals, you compute if you have enough photons, you compute the spectrum, the spectral peak energy, and the flux or luminosity if you have the redshift in each interval, and you can obtain what you see on the left. You even don't need the redshift in this case, and you see that here each diagram is a single gamma ray burst. No? So before each point in the diagram, a peak EIS or a peak luminosity correlation was a different gamma ray burst. Here each point is a time interval of the same GRB, and you see that in most gamma ray bursts, for most of the duration of the gamma ray burst, you have this correlation between spectral peak energy and flux. And if you have the redshift, you have on the right, you convert the flux into luminosity, and you see that all these points of all these gamma ray bursts tend to stay on the same peak luminosity correlations. So this clearly gives a very strong support to the reliability of this peak intensity correlation in gamma ray burst, of course, because if one can imagine selection effects that affect the correlation or shape the correlation when you consider different gamma ray bursts, it is much more difficult to imagine selection effects producing such correlation inside the GRBs, and at the same time, of course, provides further clues on its on the physics. Okay, I don't go through again the physical, the relevance of the PKIs or the peak luminosity correlation for the physics, because Dean is already gave a very nice review. Of course, he's very much an expert, and as he said already in 2002, himself and Mezzaros, I think that Zhang and Mezzaros published a very nice overview of the models of the different scenarios for the propagation of gamma ray burst, and depending also on the magnetization degree of the fireball, for instance, and how the peak luminosity or the peak radiated energy and the peak radiated energy Lorentz factor correlations can be produced in each of these models. So I just mentioned, of course, that this correlation is also very much used for identifying and understanding different subclasses of GRBs. We know very well that in the peak isoplane and also in the peak luminosity plane, long gamma ray burst and short gamma ray burst tend to populate different regions of the plane, and this is often used as a method, one of the methods to understand if a gamma ray burst, in addition to the duration, can be classified as short or long, intrinsically short or long, if it is a type 1 or type 2 gamma ray burst, or if you wish, a collapsor gamma ray burst or a merger gamma ray burst. And of course, this correlation extends also to the X-ray flashes. And also we have these points like the famous GRB 980425, which is the prototype of the long GRB supernova connection, and it is an outlier of this correlation. And as is seen on the right, like other gamma ray bursts, now I show 980425 and 031203, these are historical GRBs. But of course, this gave rise to a big of discussion on the possibility that these gamma ray bursts that are underluminous are also seen off axis. So they may be false outliers of the correlation, as they are very nearby. And as for the short gamma ray burst, 1708-17, that was associated to the gravitational wave signal by LIGO, from neutron star to star merger, a very famous event, was also seen off axis. So this demonstrates that actually, especially for nearby gamma ray bursts, of course, if gamma ray bursts are actually collimated into jets, as there is much evidence, even if we don't know the degree of collimation of the jet, we expect that local gamma ray bursts are mostly seen off axis, and we have this kind of effects. So let's now focus, after this long introduction, on the possible use of gamma ray bursts. So now we have, for cosmology, we have this correlation between an observable, which is the spectral peak energy. You simply compute the spectral peak energy in the cosmological rest frame, shifting by 1 plus z, the redshift. You have the fluence or the peak flux. You compute the radiated energy or the peak luminosity using the redshift, but of course you need the luminosity distance, which contains, of course, the redshift, but also the cosmological parameters. So H naught, for instance, omega lambda, your cosmological model and the cosmological parameters. So now, if we wish to use this correlation for cosmology, so which means extrapolating the radiated energy of luminosity from the spectral peak energy in very rough terms, of course, we are going into a kind of circularity, because to discover or to compute this correlation, the parameters, the slope, the dispersion, the normalization of the correlation, we assumed a standard cosmology or a fiducial cosmological model, of course. So now, if we are trying to use this correlation for cosmology, we are going to famous circularity. How can then we avoid circularity? Well, we start from a very basic method, and this is what we did in 2008 with the first work using the peak isocorrelation for cosmological parameters, in which we ask ourselves, but how does the goodness of fit or the dispersion and the goodness of fit of the correlation vary as a function of the cosmological parameters that were assumed in computing ISO? Or, very simply, very first exercise, we assume a flat lambda CDM model because we have evidence from the CMB, the prediction from the inflationary scenario, and also type 1 supernova and so on, that the universe, no, not type 1 supernova, just the CMB and the inflationary model, that we are living in a mostly flat universe. So we live free to vary only omega m by assuming omega tot equal to 1. We compute the peak isocorrelation for each value of omega m from 0 to 1. And what to do, we measure each time we fit the correlation, we measure the goodness of fit. What to do, we obtain is a very nice parabolic shape of the chi-square, if you use the chi-square as a goodness of fit method, for instance, which minimizes at omega m 0.3. And if instead of using the chi-square, we use a more proper method to characterize the correlation, as I already mentioned before, which is this one of these likelihoods, which parameterize also the dispersion of the correlation, we can not only again confirm that the gamma ray bursts through the peak isocorrelation are sensitive to, can provide us clues to the cosmological parameter, but that this indication converge to omega m around 0.3, and we can also use, of course, this likelihood to get a confidence level, to give an estimate of the uncertainty on this measurement. So it's not qualitative, but also quantitative. And I say this is a very simple analysis, but it's also very impressive, because if we didn't have type 1a supernovae, this is more than 10 years ago, type 1a supernovae, but only in the assumption that the universe is flat, as the CMB is telling us. And
Lorenzo, can you wrap up, because the time is up and we need to leave also time for other speakers. Thank you.
Okay, so, and very simply, gamma ray bursts by themselves through this correlation are showing us that if the universe is flat, omega m is around 0.3, and so the universe must be accelerating. And this is an independent evidence, completely independent of type 1a supernovae or other baryonic acoustic oscillations and so on. So I think this is a very strong, evidence, important evidence from gamma ray burst and for the cosmological use. Of course, if you increase the gamma ray burst in the sample, you get contours in the omega plane, you have more tight constraints on omega m. If you put them gamma ray burst on this old omega lambda plane, you get this kind of contours already somewhat competitive with type 1a supernova clusters. And these are the expectations as a function of number of gamma ray bursts in the sample. Now, as I said, we have more or less 250 gamma ray bursts, and we have this accuracy on omega m. And if you assume also a fiducial value of omega m, you can investigate the value of W0, the equation of state of dark energy. But so I'm very late with this. So I just mentioned that, of course, gamma ray bursts can also be calibrated against type 1a supernovae, as several authors also did. So as the type 1a supernovae are calibrated against Cepheids, gamma ray bursts can also be calibrated against type 1a supernovae up to ratio 1.4 and can be used to get already very sensitive measurements, not only of omega m, but also on the equation of state of dark energy. So these are my conclusion. Of course, we expect much more progress on this side, and also from other correlation with the extension of the sample, the better understanding of the physics and the collimation degree of the gamma ray bursts, which actually is really mostly unknown. So I think that all the efforts that the community is doing for exploiting gamma ray bursts for cosmology through this correlation and other correlation are very worth to do, and maybe and will be very much complementary and useful to other studies like Euclid or future investigation of the dark energy. Thank you so much.
Oh, thanks very much for this exciting talks. Any questions? Sorry, only one question because we have not much time.
I think we should continue, and the question maybe will be later for Lorenzo privately, because we are running out of time. Thank you.
Okay. Thank you. Thank you again. So let's keep going. The next speaker, Professor Yonghong Wang. He will talk of search for the string quark polyins. Welcome.
Okay, I will try to share my screen.
Okay.
Okay, can you see it?
È andato un po' lungo, ma
okay.
A me mi sono sentito abbastanza bravo.
Lorenzo, can you please mute your microphone? Thank you.
Okay, can you hear me?
Yes, yes.
Okay. Good morning, everyone. First, I would like to thank Maria and Dr. Li Liang for organizing this very interesting session. My talk is about strange quark planets. Where the topic of this session is about GB correlations. Professor Zhang Bin, MIT, have presented a very interesting review about the correlations, and later SF will also present his lecture also on GB correlations, and my student Xu Fan will also present our study on GB correlations. These correlations, actually, many of these correlations support the idea that although some GBs may be produced by black holes, but still neutron stars or magnetars could be the central engine of some GBs. So in my talk, I will discuss the internal composition of neutron stars. Especially, we discuss the possibility that these neutron stars actually are composed of strange quark matter. This is the outline of my talk. First, I will briefly introduce the concept of strange quark stars. I then discuss how to discriminate between strange quark stars and neutron stars. And in the third section, we present our recent studies. We argued that we can try to identify strange quark objects by observing strange quark planets. So first, let us see what are strange quark stars. We are very familiar with pulsars and neutron stars. Pulsars are usually believed to be neutron stars. This is the diagram showing the internal structure of a neutron star. We have outer crust and inner crust. And we also have outer core. But for the inner core of neutron stars, since the density is very high, it can be several times the nuclear saturation density. So the composition here actually is largely uncertain. This figure shows the many of the possibilities. There could be Kerr or pair condensation, and especially there could also be the internal, especially this compact stars can be composed of UDS quarks. So in this case, we call the compact star strange quark star. This is the this figure shows the difference between a neutron star and a strange quark star. For a neutron star, we can have many neutrons inside the star. But for strange quark stars, it is mainly composed of quarks, especially U, D, and S quarks. It's very interesting that if strange quark stars can exist, then we can have a sequence of strange quark objects. This figure shows the mass and the radius relations for neutron stars and compared with strange quark stars. So we see that similar to neutron star, we can have strange quark star, but we can also have some less massive strange objects. For example, comparing with normal white dwarfs, we can have strange quark dwarfs, and we can even have strange planet whose mass is similar to our Jupiter or our Earth. In fact, there are many papers discussing the concept of strange quark stars. These are some early literatures. So since pulsars can be strange quark stars, how we can discriminate between strange quark stars and neutron stars? At the first glance, it seems that strange quark stars should be slightly more compact, and they should have smaller radius. But to discriminate them by observations, it is still very difficult. Some methods have been suggested to discriminate these two kind of compact stars. For example, they have for a 1.4 solar mass compact star, they should have different radius. They should have different mass and radius relation on the MR plot. They may also have different maximum mass, and their cooling rate may also be different. And the maximum spin they can also spin. Their maximum, their minimum spin period may also be different. But observationally, if you want to discriminate these two kind of stars by this method, still it is very difficult. For example, the mass and the radius observations for pulsars is not accurate. In this figure, we can see the mass and the radius error bars are very large for these objects, so they cannot be used to test the equation of state. So for other methods, there are also many difficulties, and these two stars can not be discriminated easily. So in our recent studies, we suggest that we can try to use strange quark planet to test these two kind of stars. As mentioned before, we can have strange quark stars. For strange quark stars, if they are bare strange quark stars, I mean, if there are no crust cover the strange core, then the density of the planet will be very high. It's about 10 to 15 gram per cubic centimeter. So for a strange quark planet, it will have very small radius. In this table, we show that if a strange planet have a mass similar to our Earth, its radius will be less than 100 meters. So even for a strange planet similar to our Jupiter mass, its radius will also be several hundred meters. So it's very compact. So what is the consequence of such a compact planet? Well, if a normal planet is moving around a pulsar, the planet cannot be too close to the pulsar, since it will be tidally disrupted if the orbital radius is too small. But if the planet is a strange quark planet, it will be very different. in this case, the strange planet can be very close to the pulsar, and but will not be tidally disrupted, since itself is very compact. So in our recent study, we suggest that we can try to search for close-in exoplanets. If these planets have orbital radius less than 5 times 10 to 10 centimeters, the planet will not be, could not be a normal planet. It must be a strange quark planet. We know that here now we have several thousand planets have been observed. So among these exoplanets, we have tried to search whether any very close in exoplanet have been observed. We have plotted the radius of this known exoplanet. We find no planet have orbital radius less than this critical value. For those many planets without density measurement, we assume they have a typical density of 8 gram per cubic centimeter, and then we plot their mass versus their radius to say whether they are being in the tidally disruption zone. We see that most of these exoplanets are in safe zone, but we really found one planet. If this planet have such a low density, it should be tidally disrupted. Actually, this planet is around this pulsar. In fact, this pulsar planet is very special. It has a mass of about 1 Jupiter. Its orbital radius is very small, and its orbital period is about 2 hours. So for this planet, for this planet to be stable around its host pulsar, its density must be high. Actually, Howard has already argued that this planet could be an exotic object. We know that currently only about 5 pulsar planets have been observed. In our recent study, we have tried to search for more pulsar candidates and to see whether they have whether any close-in planet have been detected. We have proposed some candidates. For example, these 2 pulsars have a companion with a very small orbital period. But the only problem is that their companion is still relatively massive. They could be about 10 Jupiter mass. So we still could not expect the possibility that these companions are actually small white dwarfs. Anyway, we believe these objects are interesting candidates and should be monitored in the future. So we proposed that we should use our radio telescopes to try to search for close-in pulsar planets, especially with a radius less than this value and with orbital period less than about 6,000 seconds. We have also if strange quark planets do exist, when the strange quark planets merge with its host pulsar, they can emit a gravitational wave at the final stage. We have calculated the gravitational emission from these systems. We found that if such a merge happens within our galaxy, the gravitational wave singular can be well detected by advanced LIGO. And even if these events happens in several MPC distance, this still can be detected by future Einstein telescope. So we call people to pay attention to this strange gravitational burst event. If people detected a gravitational burst from a neutron star and a planet, then the planet should be a strange quark planet. Recently, we have also tried to search for strange quark dwarfs. We know several tens of thousands of white dwarfs have been observed. Their mass and radius are measured. For these so-called white dwarfs, we have tried to check whether some strange dwarfs deviate from the mass radius relation for normal white dwarfs. Yeah, as a result, we do find 8 candidates. Their mass radius do not match the radius for normal white dwarf, but can be fit by strange dwarf. So we argued that this may be a strange quark dwarf candidate. So finally, I give a summary of my presentation. So strange quark matter could be the true ground state of hadronic matter. In this case, pulsars may actually be strange quark stars, but not neutron stars. So strange quark planets may also exist. These strange quark stars planets can be identified by searching for close-in planets. And the gravitational wave emission from strange planet and its host may also help to identify these strange quark objects. Okay, thank you.
Okay, thanks very much to Professor Wang. He was so excellent talks. Any questions? Only one question, sorry. Any questions?
Yeah.
Yes, there is a Asaf.
Okay.
Yeah, thank you for your talk. I can understand that strange stars could emerge out of a collapse of a massive regular star. How would you envision that the strange star planets would form in the first place?
Okay, yeah, okay, thank you for your question. This is a very interesting question. Where strange quark planet how can be produced? We thought there are maybe several possibilities. First, if a strange quark star was produced after a supernova, the newly born quark star itself should have a high temperature. It may also be fastly rotating. So it is possible that a part of a clamp may be ejected from due to the fast spin, and very similar to our moon was produced was ejected from the Earth. This is a possibility.
Okay, thank you.
Okay, thank you.
Thanks to the speaker again. Let's keep going. The next talk, Professor Xiangyu Wang. He will give a talk on the origin of the very high gamma ray from gamma ray burst. Okay.
Okay, so can you see my slide?
Yes.
Okay. Okay. So, first, I would like to thank Liang and Maria for the invitation. So I'm going to talk about the very high gamma rays. So topic maybe kind of different. So my name is Xiangyu Wang from Nanjing University, and the work is in collaboration with Luyu Liu and Professor Bing Zhang. So this is my outline. So basically, I will talk about first about the Fermi observations of gamma burst. Then I talk about the recent TV observations of gamma burst and possible interpretations. Okay, so as we know, the Fermi already detect a lot of gamma burst. So there's a large air telescope, so which can detect gamma rays above 100 MeV up to 300 GeV. And in 10 years, so Fermi already detect about 180 gamma burst. So this shows this E peak as a function with fluence. So, and you see here these bright dots are the light detected burst. So for long gamma burst and red for short gamma burst. And these dark dots show this gamma burst detected by GBM. So basically, the brightest gamma burst are more likely to be detected by Fermi light. Okay, so this shows two examples. So of the light observation of gamma burst. One is the short gamma burst, GRB 090510. So you see here. So this is a light curve, so which extend to about more than 100 second of the burst. So this is the primary emission phase, which is a short gamma burst. So the light emission is much longer than the prompt emission phase. So for this, is a similar case for the long gamma burst. So we see here, this is a proper KeV MeV emission. So given by this black curves here, for this light emission given by the red one, so which extend to more than 10 kilosecond. So we see that the high energy emission is much more extended than the proper emission phase. So then people propose that this extended high energy emission is produced by afterglow. So just similar to X-ray and optic afterglows. So as this is for the short GRB 09510. So we see this X-ray and optic afterglows together with these Fermi light curves. So Kumar and Dorner suggest that this simple afterglow model can explain the both extra-optic and high energy emissions. So this is quite a similar scenario to explain this high energy emission, extended high energy emission. However, there's one issue for this synchrone scenario for the late or extended GB emission, because we know that there's a maximum synchrone energy. So there's a maximum limit. Typically is 50 MeV in the short rest frame. So this is under assumption of the Bohm acceleration approximation. So then consider that this is the by-growth factor of gamma, the maximum energy observed in the by us in the observed frame by us. So then would be like this. Typically will be 5 GeV at 1 to 10 per second. Okay, so this is not much large. This is not large enough because we already Fermi already detect photons above 10 GeV. So many photons above 10 GeV. So this seems to challenge the synchrone scenario. Okay, so as already suggested in these papers. So if we consider that the Bohm approximation maybe breaks down in the GRB afterglow because for microturbulence magnetic field, so typically the coherent length is like this. So then the lambda radius will be much larger than this coherent length, which means that we cannot use the Bohm approximation anymore. So then this will lead even to a lower maximum energy for synchrone radiation. So then the people suggest that maybe some other models can produce even higher synchrone maximum energies. For example, people suggest that maybe the radiation zone is different from the acceleration zone. Then we will not have such an uplimit. So is this will be work? So I think this is still a question. So from observations side, so we already see that many photons with energy up to 100 GeV detected by Fermi. So we see this is for this bright GRB, the maximum the photon energies as a function of time, and these lines just show this maximum theoretical limit, the limit for the synchrone energies. So you see that many photons actually above this theoretical limit. So this poses the question: what mechanism produce these high energy photons? So a natural scenario is that maybe these photons not from the synchrone radiation, just from the inverse compton radiations. So as we already see that in AGNs, right? So in AGNs we typically see a synchrone component and an inverse compton component, and this inverse component could be synchrone self-compton emission or even external inverse compton emissions. So there's some papers already discuss this. So for this, I mentioned that this is a very bright GRB, and GRB 130427A. So we analyze the latter data. This is energy distribution. So at a different time. So basically, you see that there's a signature that of a hardening of the spectrum above, like the GeV, right? At the time of this at late time given by these brown dots here. So this signature is has a significance of 2.9 sigma. So it's not very strong. So as the Fermi calibration, they argue that this may not be a spectrum hardening. There may be just a global spectrum hardening evolving with time. So that suggests this possible scenario. So this will need to be decided. So by more data, the best will be for the TV data. Okay, so we also explain this the spectrum data line up with synchrone plus inverse compton scenario. So the left is modeling of the spectrum, and the right is a modeling of the light curve at the different frequencies. So generally, this synchron plus inverse convolutional model can fit the data destiny where. So however, I want to say that this is still inconclusive yet, because this significant hardening just 2.9 sigma. So we need clear evidence from the TV photons. So for the TV photons, there are already a lot of efforts in searching for photons above 100 GeV with a Cherenkov telescope, because with this Cherenkov telescopes, we can detect the shower produced by the very high-energy photons. So this detection includes like Hess, Magic, Veritas, and other detectors. And this is going to be not easy, because as you see that as of 2016, Magic observed almost 19 GRB in good observed conditions. However, they do not detect TV emission from this GRB. And also this for Hess, so this shows this Hess detections of many gamma bursts. So it seems that a long time Hess also do not detect any gamma burst. The things changes in, I think, in 2018. So Hess detected one gamma burst, GRB 180720b. So you see here, this is the detection here, but later on, the disappears. So the detection observation started very late, is 10 hours after burst. So this shows this is a light curve. This red dot is Hess observations, and they also show other observation at other frequencies, like the, for example, the optical and also X-rays. So X-ray emission actually is very bright. So, and this GRB is relatively nearby because it has a redshift of 0.6, so it's close GRB. And then in 2019, Magic also detected GRB 19014C. This shows is magical detections. Magical detections started from about 60 seconds after burst. It lasts until to 2 kiloseconds. It's given by here. Okay, so this is a magical data, and also X-rays. They have the X-ray very bright X-ray afterglow. Okay, so it lasts more than almost 1 day, I think. So again, this is also a nearby GRB. So the redshift only 0.4. So because for GRB high, but TV photons, there's also the one problem for the EB absorption for this cosmological GRBs. As you see here, this is absorption attenuation as a function of energies. So only with nearby GRB we can possibly detect the high photons. So this shows this is a EBR correct spectrum and the EBR and the observed spectrum. So you see that the correct spectrum actually is quite hard. Okay, so I think there are several absorptions. I just mentioned EBR. There are also the other absorptions like internal gamma absorptions, because in the source, within the source, there are also low energy photons. And for inverse common scenario, there's also another effect is called a Klein-Nichel effect. The high energy photons, they also have this kind of effect. So it's not easy to produce or observe these TV energy photons. Okay, so for the internal gamma absorption, the TV photons will interact with X-ray photons typically. So this is op depths. So we are depend on this lambda density of the target photons. Okay, so if we need to the small op depths lower than 1, we will need a high Lorentz effect. typically we have high noise effect. Then we can transform to the, we need a low density of the instant medium. So typically like this, goes like this. So this will put constraints on the environment of the gamma ray burst that can produce TV photons. And another effect, as I mentioned, is the Klein-Shiner effect, because high electrons, they have, if the photons seen by these electrons were above the MGC square, they will go into the Klein-Shiner scattering regime. So this is because it is a break, Klein-Shiner break. The typical energy goes like this. So if we need to photons like for example, about 1 TeV, we need a very small epsilon b, which is a equalizing factor for the magnetic field. Okay, so this is constraints. So we perform a modeling of this gamma ray burst with broadband modeling. So that we already know that this will consider the dynamics and also radiation mechanisms, and also we need to consider these input parameters. So then the Plateau goes into the industrial medium, produce a synchrone or inverse common radiation. So with this model, we try to fit the data of these two TeV detect gamma burst. So this is for GRB 180720B. So basically, we can fit both LED, X-ray, and optical, and also this is a Hess observations with this kind of parameters. And here, we show the spectrum. So typically, this is a synchrone component, and this is a inverse component. Okay, so this for 14C. So this is also detected by TV detect GRB. So we also model this multiband light curve and also the SED. So for this GRB, we also analyzed the formula data. So we found that the Fermi data, there seems a hardening here above the 1 GeV. So this seems to be consistent with these magical detections. So later on, magical reported their result. So shown here, so show the SED. So you see that this is magical detections. So after EBR corrected. So basically, they also have the two components. One is the synchrone component, and another one is inverse component. So the TV emission is produced by the inverse component. So this is generally consistent with our modeling. And here this is a Fermi data just falling on the between of this of the two components. Okay, this is a GRB as a paper is recently published. This is GRB 190829A, which is very, very nearby GRB. And some people call it this low limit GRB because it's the astropic energy is only 10 to the 49 ergos. So this is show the spectrum by Hess. So basically, you see that this is X-ray, the X-ray spectrum, X-ray here, and here is Hess observations. So the Hess paper argues that this the TV component is just lies on the extraporation of the X-ray component. So they can simply explain with one component. So then they propose that there may be this one component is synchrone radiation. However, this will put the maximum energy for synchrone scenario even to higher energy. Now is to the TV. So this is still a problem. How to produce such high energy photons with synchrone scenarios? So of course, people also try to modeling with the synchrone plus the inverse common Silanians. This is given by this blue lines. However, as argued in this paper, seems that I do not find that this can explain this TV data. They argue this Klein-Shinner effect will be important, so they have a steep decline here. Oh, I forgot to mention that X-rays and TV and have a quite similar slope, decaying slope. So this also a kind of evidence that support maybe that from the single component. Later on, there's another paper proposed that, okay, so this is modeling with the data with synchrone plus inverse common Silanians. They explain this Hess data with still with the inverse common Silanians. So this is quite, I think, the more traditional model. So in this, when they embed data, they will need that only a small fraction of the electrons are accelerated in the shock. So you see here, this is a fraction. So only 1% the electrons are accelerated. So they will need a large total energy in the ejector. Okay, so also briefly also mention that LASO detector, which is a very high energy gamma detector in China, in the west of China. So LASO they have a water channel curve detector, so WCDF. They also observed this GRB during this prompt phase. So this I think is very interesting because this WCDF is has a white field of view, so they could monitor some GRB. So interestingly, they modeling the prompt emission. So and unfortunately, they do not give the detections, but they have a uplift here shown by this. I think this is a green one. So this is up limit at TV energies for the prompt emission. I think that this will constrain the Y parameter for the prompt emission phase of the gamma burst. Okay, so I go to my summary. So basically I think that the GRB studies are now entering the TV energy domain. So thanks to the Cherenkov detectors and the radiation mechanism for the TV is still on debate. And some people suggest this is synchrone Silanians extend to very high energies or inverse common Silanians, or even maybe possibly the hydronic Silanians that can produce also the TV emissions, but this will need a very large energy budget. And the detection of the TV photons will shed more light on the physics of gamma burst, such as particle acceleration, and also maybe also study the EBRs with the gamma burst in the future. Okay, so thank you very much. So I stop here.
Okay, thanks so much. Any more questions? Sorry again, only one question. Sorry. Okay, if not, let's us to move to the last speaker.
Thank you.
Thanks to Professor Wang again. Sorry.
Yeah, so just let me stop sharing. Just
okay.
Want me to here.
So Liliang, either we can have a break now and have Asaf and Uzne have their two talks together,
okay.
What do you think, Asaf? Do you prefer to have a break now, or?
Yeah, we can have a break now, a few minutes.
Yes, yes. So let's. Okay, so let's have a break of 5 minutes. So we will reconvene at 21, and we will restart again with Asaf and Uzne.
20.
5 minutes.
5 minutes. No, 5 minutes. 5 minutes, Liliang, because we are, behind the schedule. Okay. So see you in 5 minutes.
Okay, thanks. Okay.
Okay, please tell me when you want to start.
Yes, so I think we can start. So welcome back to the second part of the second day of GRB correlations and observational challenges and the theoretical implications. We have the pleasure now to have Asaf Peer speaking about theory of the plateau phase in gamma ray burst. Thank you, Asaf.
Oh, just a second. Can you see my screen?
Yes, we can.
Okay, since everybody seems to be muted. Okay, let me just do that. Okay. So yeah, so thank you very much for inviting me to give this talk. I'll be talking about theory of plateau phase in gamma ray burst. That is a project that is led by Husne Dereli Begue, who's working with me now, and of course with Felix Wright, as well as Maria and Bing. What happened? Yeah, okay, there it is. So the X-ray plateau, which is not new really, right, is something which was new and we've seen right after the launch of the Swift, which was back at the end of 2004, and already in 2005, people have noticed this phase, what's called phase 2 here, the plateau. It's a very ubiquitous result. And interestingly, it was not expected at all, right? When you look at what people have thought the early afterglow would look like, Then people have expected the self-similar expansion, which is described by the Blandford and McKee solution, in which the X-ray flux should decay as, depending on the power law, P is the power law index of the electrons. So roughly like T to the -1, or maybe slightly more than 1, depending on the power law index of the electrons. And at the later times, there was this jet break, which was anticipated, which will cause a steeper decay. The important thing is that nobody has expected this phase. So what we're seeing instead of that, as you know, is just following the prompt, there is a sharp decline, which is followed by this plateau phase. Can you see my mouse, by the way, which I'm using as a cursor?
Can. Yes, we can.
Okay, very good. Now it's just gone, right. Rather than we're seeing this plateau, and there are some flaring, which also helps things, blur things. And only after that, after something like, a few thousands of seconds or so, we're seeing this, what we basically expected afterwards. And of course, these puzzling results led to a plethora of ideas, which being in this very nice talk, touch upon some of them. I tried to make a full list of them. And there is something in common to all of them, which is, they require some modification of the standard classical fireball model, which was at that time pretty much well established. So we're talking about either some sort of an energy injection. There is something else, like being showed at NUSEC as proposed back in 2006. So continuous energy injection that may slow down the acceleration. Maybe the jet has some, two components or some geometrical effects. We have a two-component jet. Maybe there is something with the medium, forward shock emission in inhomogeneous medium. Other options that related to the medium, something must happen there, right? So scattering by dust or modification of the density, possibly by some early trigger that might have been there. Other proposals suggest that dominant reverse shock emission, maybe the microphysical parameters that determine the magnetic field and the energy of the electrons vary with time. Maybe there is some viewing angle, maybe we're seeing the jets off axis. This is something which was proposed quite early on. I mean, when you see that the dates here, most of them are going back to 2006, 2007, shortly after this detection. And people are still continue to work on that, right? Recent works, Oganessian and Beniamini, just from last year or so. And then there was this idea that maybe there is a forward shock before the deceleration by Shannon Matzner. Now, again, when you look at it, pretty much all of these models, except from the last one, require some additions or modifications to the simplest scenario, which seems to be working quite well, and that's what everybody has expected. Except from the last one. So when we look at the last one, it did have some requirements, right? One is that the explosion cannot be into a constant density interstellar medium, but rather into a wind ejected medium. The second is that it flows from their analysis and from other people as well, is that the Lorentz factor they found is somewhat smaller than a few hundreds, even smaller than 100, which people criticize as being inconsistent with what we know about the Lorentz factor of gamma ray bursts. And another criticism that appeared on that work was that it cannot explain achromatic breaks. Now, we actually developed it, I should say quite shamefully, independently, but then we looked at this paper and we realized that, in fact, there is something in there. So the first criticism is about gamma. So the criticism, just reminding, was that it requires Lorentz factor of less than 100. But the first question is, how do we know what is the Lorentz factor of gamma ray burst? So, we cannot really know, we cannot measure it, but we can infer it indirectly. And there are three main ways. Really interestingly, Bing gave a very similar slide in his talk earlier on today. So the first, of course, and the most useful one is the opacity argument. The fact that we're seeing LAT photons or GeV photons, namely photons which are above the threshold for pair production, necessitates high Lorentz factor in order to avoid production of pairs. And this is something which was noted very, very early on, early in the 1990s, and people are still using it. The second method is identification of the onset of the afterglow, right? Or the reverse shock, if one can identify it, or when the flow becomes self-similar. And since we know the similarity conditions by given to us by Blandford McKee, then we can infer the Lorentz factor if we happen to know what is the energy or the density, but the dependency is very weak, so it's not really important, but mainly the time. So it goes roughly as time to the -1/2. So if we can identify at what time we are transitioning to self-similar, we can get some estimate of the Lorentz factor. The last one, which is later than the others, is the identification of the thermal emission. Very shortly, right? Thermal emission is something which we generally expect unless we don't see it because of adiabatic losses. In other words, we want it to occur quite early on. We want the photosphere. This is the location where the thermal photons get out of the plasma to be closer to the acceleration, because otherwise we'll still see them, but it will be, they're going to automatically. And so the observed temperature is very strongly dependent on the value of the Lorentz factor. So if we want to associate the peak to the thermal emission, that gives us pretty strong constraint, maybe too stringent in some sense, on the Lorentz factor. So now we can look at the data. And here is something very interesting that we see when we look at the data. When we look at the second Fermi catalog by Aiello et al., which was published 2 years ago, and there was another paper which I did not put in that Maria was actually first author on, we find out that when we look at the lat bursts, that basically they do not show any evidence for a plateau. Only 3 out of 186 in the lat bursts. In the second paper, it was only 3 out of 148 bursts of lat bursts show evidence for a plateau. So there seems to be anti-correlated. In other words, the opacity argument is not valid for these plateau bursts. The second point, we didn't go through all the sample because it's quite lengthy and the quality of the data varies. But the NDP line, this is the line that defines the non-dissipative photosphere. This is where we're certain that there is thermal emission. And we're pretty much seeing that, I put plus minus because I'm not sure it's all of them, but definitely the vast majority of them, of bursts that show evidence for a plateau, actually do not show evidence for a leading thermal component. So there may be some thermal component, but it's certainly not a leading one. Which means that all the indications we have that for high Lorentz factors simply do not exist in those bursts that show a plateau. So the plateau burst seems to be anti-correlated with the information that we have that requires high Lorentz factor. Such requirement actually does not exist in this burst, which is pretty interesting to see. Now, in order to understand what we might be seeing, that's the very sketchy basic of the dynamics, right? So the basics of the dynamics simply say that there are 3 distinct phases. The first phase is the acceleration. The second phase is the coasting, where the explosion energy or the spin energy has been mostly converted to kinetic energy. And then during this coasting, then the emerging plasma, the expanding plasma collects material from the interstellar medium. And then when it collects enough material and it starts slowing down, and the Lorentz factor evolves with radius, depending on the profile of the ambient medium. If it's a constant, then gamma would go down as r to the -3/2. If it's a wind-like, namely that the density drops as r to the -2, then it will drop down somewhat slower, goes r to the -1/2. And during the transition between the coasting phase and the self-similar phase, this is when we expect to see a reverse shock emission. This is something which is not new at all. This is something which is basics from early times of the fireball model. And this relates to the second question that we have. So is there any evidence for achromatic breaks? So here I try to summarize basically everything we know about synchrotron. So at these times, obviously, the leading radiative process is synchrotron emission. And as you know, the synchrotron emission has several characteristic frequencies. I'm focusing on only the 2 that are mostly important for us. This is the peak one, nu amp, which depends on 3 parameters: the magnetic field, the electron Lorentz factor, and the bulk motion Lorentz factor, denoted here with a capital gamma. Then there is the cooling break, which depends on the Lorentz factor, the magnetic field, and the radius in which the energy is dissipated. And the last thing of interest is F nu peak, the flux at the peak, which depends on the magnetic field, the Lorentz factor, and the total number of radiating particles. And it's basically a textbook solution, which was there in the literature for over 20 years, showing that the expected spectrum would have several different slopes depending on the location of the observed frequency nu relative to these two characteristic frequencies, the peak frequency and the cooling frequency. The fast cooling scenario, that is the nu c is smaller than nu m, so the electrons cool down, essentially lose all their energy within the dynamical time. Then for low frequencies, it goes nu to the power 1/3. For higher frequencies, it's nu to the minus 1/2. And then for even higher frequencies, it's minus p/2. That's exactly what is plotted here. And for slow cooling, we have different, slightly different dependence. It also goes nu to the 1/3 for lower frequencies. Then it's a minus p-1/2. P is the power law index of the electrons for intermediate frequencies, and then minus p/2 for higher frequencies. And I denoted these regimes as A, B, C, D, E, and F. Now we can simply put down what we think we understand about both this, coasting phase and the self-similar phase, which are the ones, the two phases which are of most interesting to us. And again, using the very simple classical description in which we believe that the shock field itself is the one that generates the magnetic field and responsible for acceleration of the particles, then the Lorentz factor of the particles would be proportional to the bulk motion Lorentz factor times some uncertainty, nu e. The magnetic field will be proportional to the energy density times some uncertain fraction, which we call epsilon b, etc. Putting this all in, we can calculate immediately, right? During the coasting phase, gamma is constant. We can calculate the energy density. And we find out that the nu m, the peak frequency, should goes down as t to the -1. That's the red line that is plotted here. Nu c increases with time. So this is the blue line. For this, during the self-similar decay in a wind phase, the nu m drops down again. Now we have somewhat different power law index. Nu c increases again. Now again with a different power law index. The important point here is that now we can put out all these 6 regimes that we have, right? A, B, C, D, E, and F around here. And the prediction that we're going to get, there are 2 main predictions, right? I put lines, one around the optic band and one around the X-ray band. And the 2 predictions that we have is that we always expect at a certain point in time, some transition between region F, in which the observed frequency is above the cooling frequency, to region E, where the observed frequency is below the cooling frequency. That's because in all cases, the cooling frequency increases with time. So from F to E, right, or from F to E, here you cannot see it. And this transition is expected to occur in the optical data before it's going to occur in the X-ray data. So that's a very robust prediction of this model. Now, what happened? Yeah. So now, giving all this dependency, we can calculate what is the expected flux, how it evolves with time, and it's pretty straightforward. So in region F, where nu is greater than the cooling frequency, then F nu should be proportional to the T, again, just in the wind case, to the power 2 minus p/2. So with power law index of approximately 2, that goes as T to the power 0. In the self-similar decay, this is something which is well cited, right? It goes as T to the power 2 minus 3p/4, or roughly 1 if p is equal to 2. In region E, we expect that the flux should go as T to the power 1 minus p/2, or T to the -1/2. And at the self-similar decay, it should go somewhat steeper, 1 minus 3p/4, or T to the -1.25. Remember, we have this prediction that transition from region F should occur first to region E, and it should occur in the optical first. Interestingly, when we look at the data, this is the X-ray data is with the pluses, the optical data, UVOT is with the dots. You can clearly see that, right? This is the line that was made by Husne, which is, she'll discuss much more on that. And that's exactly what we're seeing. We're seeing this evolution from T to the power 0, then it goes down to T to the -1, and possibly later on. Of course, it's not that easy because we have a lot of contamination around here. There are flares and bumps. but the trend I think is pretty clear. So there is a very good match to that, which is a very good sign. And if we accept this general approach, in fact, we can get a lot of physical information, because the transition time from the coasting to the self-similar motion occurs when there are two conditions are met, when this time is much greater than the prompt emission time, and when the Lorentz factor of the self-similar one is smaller than the initial Lorentz factor. So for the wind case, it's pretty easy to show. This is the formula that the transition time depends on the energy on this A parameter, which represents the density, and the initial Lorentz factor gamma I to the power of 4. So if we happen to, and of course the redshift. So if we know the redshift, we know the energy, we know what is A times gamma to the 4 as a function of the redshift, the energy, and the transition time. In region F, where we have this flat light curve, we actually know what is the flux that is expected to be observed, right? We know what is the peak flux, which is again depends on this density parameter A, the gamma I, also on epsilon E, and of course the distance. Which means that if we know the transition time and we can identify this as a flat spectrum, then from knowing the energy, the flux in X-ray, the transition time, and the redshift, that gives us a full solution that gives us what is this uncertain microphysics parameter epsilon E. Now, in case that the optical flux decays, namely that the optical flux in region E, and I want to remind you again, we expect the optical to transit to region E way before the X-ray flux, then we know how the optical flux should decay, and that gives us a second constraint, which would relate the values of A star to some power gamma I to another power n epsilon B, give us some value. So we do have a full solution for this microphysical parameter epsilon E. We do have a degeneracy on gamma and A star, but possibly we can partially break it, assuming we know what is this value of epsilon B, the fraction of energy that goes into the magnetic field. And here, this is a physical guess that says that this is a universal. That it should not change in between the different regimes, as long as we're in the relativistic regime. So this is an example of what we did here, right? This is one example which I already showed. The Kusner is going to show plenty of more details of how it's been done and more examples. This is 1 GRB 091029. We know what is the energy. We know what is the X-ray flux. We know what is the flux at the R band at a given time. We know what is the break time. And when we plug in all the values, we got that epsilon E is 3 times 10 to the minus 2, very close to the fiducial value. I want to remind you that these fiducial values are derived based on old afterglow emission, so very late times afterglow emission. And here we get a completely different method, which give us a very similar result. So that's very encouraging, of course. And then using the values of A times gamma to the 4, and then this second constraint from the optical, again, we have basically 2 equations with 3 parameters, so we cannot fully solve it. But if we assume that we know what is the value of epsilon B, then we can solve it. So if epsilon B is 10 to the minus 2, then we end up with Lorentz factor of 65, somewhat lower than what many people think. But again, I remind you, there is no contradiction. If epsilon B is larger, then gamma is larger, but that at the expense of the ambient density is much smaller. We're talking about something between 10 to the minus 3 or maybe even 10 to the minus 4, something like that. So much smaller. In a Wolf-Rayet star, as a reminder, we expect it to be of the order of unity. So to summary, I'm pretty much running out of time, I believe. The existence of Plateau puzzles the community for more than 15 years. The Plateau bursts, and these are observational evidence, do not, by large, show any emission in the lat energy band, so no GeV emission, do not show strong thermal emission, which is an indication that initially the Lorentz factor is lower. And the Plateau is naturally interpreted as emission during the coasting phase. There is no contradiction. There is a closure relation between the temporal and spectral evolution. So Kusner will talk about that in the next talk. During the Plateau and immediately after the Plateau, that gives us another, strengthening the point, basically. It's another indication that we're on the right track, which means that we are consistent with the same power law index of the electrons. and the different and that at the same regime, so F and E. We do not expect, the F and E represent a change in time really, but they do not represent a change in the microphysics of the electron's acceleration. So we don't expect any change there, and we don't see it. The values of the universal microphysical parameters are consistent with what we're seeing in other phases. And so the consequences is that the gamma I of these plateau bursts, and I remind you, this is something like 60% of all bursts. So many of them are only few tens, it's not few hundreds, which essentially fills in the entropy gap. This is a very question that I was wondering about for many, many years. How can it be that in AGNs, the Lorentz factor is, a few, maybe up to 10, 20, and in GRBs, it's hundreds. What happens in between? What happens in between 10 and 100? And I think we found a solution here. And the price we pay is that the ambient density, A star, what we call, is much lower than people think. So, in a Wolf-Rayet star, most people expect it to be something of the order of unity. We find something more like 10 to the minus 3, which means that two options. Either it's not a Wolf-Rayet progenitor, but other progenitor. The alternative is that it is a Wolf-Rayet progenitor, but we don't really understand what happens to it just in the last few years prior to its final explosion as a gamma ray burst. So we don't really understand the final stages of evolution of these stars. If I have to put my money, I likely put it right here. So that's what I had to say about the theory, and more on the data analysis and the consequences and the implications of all that is going to be right now with Husna.
Okay, thank you so much, Asaf, for your very nice talk. And maybe we have time for one quick question, if any. I just want to, so if there are no questions, I just want to, there is a question?
I have a blue hand in my chat box.
Okay, so please go ahead. Sorry, I didn't see you.
Question / comment, Asaf. We briefly spoke about this offline as well, but since it's Maria that I'm also seeing on my screen, those correlations may come into play here in this conversation. And a paper that I wrote a few years ago actually delves into this whole deceleration stuff. I can put a link on the chat as well. But one thing that I found was that if you want to make this system work with decelerating blast waves and so forth, and also obey those cross correlations between flux and plateau end times, both in X-rays and optical, you are effectively moving towards a thick shell scenario in the parlance of whether or not the reverse shock managed to get relativistic. It's not necessarily about emission from the reverse shock, it's just about the dynamics overall. So I would suggest you also check whether or not the physical values you get out from the data analysis end up in the thick shell scenario or in the thin shell scenario. Because it's not possible from if you look at, say, population studies to actually get this kind of correlation from a thin shell scenario.
I completely agree with you. I looked at the paper and I think we end up with a 6 shell scenario. I think you're right there.
Okay, that and potentially is a fairly strong statement, because what is then making this into a thick shell scenario? It could also have implications for the remnant nature, for example.
Possibly, yes. A thick shell essentially means that the prompt emission lasts pretty long. So, you have a pretty lengthy, thick shell at the end, right? There is ejection that lasts pretty long. But we know it is because we know that when we look at the prompt emission, it lasts typically in these bursts, 10 or tens of seconds. So it's not that surprising.
Well, that means that you exclude short GRBs from the conversation that way, which can also have plateaus.
This I have to check, because this is, this is something which is obviously very new, and Husna will speak more about that. I mean, we don't have the quality of the data that we have. We do it. We try to be very careful here, because although 60% of GRBs show evidence for plateau, those GRBs, and there are a lot of interfering, missing data, flares, no data in the optical, no redshift, no many things. So Maria actually, I think, spoke about that there is this gold sample which we took from there, and even there, not everything could be used. So yeah, I don't know if we have any short GRB, maybe one in the sample. I'm not even sure about that. You're right. I mean, there is a room
probably
for
090510. Probably 090510. It is a short with extended emission. Yeah.
Yeah, this is the one exception that we have. I think Husna was maybe speaking about it. I'm not sure.
Of course, a way out would be, but I don't want to hold up the crowd here, but a way out would be to have a long-lived remnant type, a magnetar, for example. I don't carry torch for magnetars per se, but that would be one way out here.
Possibly. I will take it, absolutely.
Okay, there is also one very quick question by Don Warren that how does this costing phase interact with the idea of a magnetar central engine adding spin down energy? So it's related to the last comment that you made. If you want to comment, Asaf, on that.
I'm not sure. I need to think about that. I don't have a ready-made answer. So I'll think about that and I'll answer later.
Okay, so thank you very much, Asaf, again for your very nice talk. And we move on to the next talk by Usna, that she will speak about the Plateau emission, GB Plateau emission, naturally explained within the classical fireball model. So a continuation of Asaf's talk.
So I would like to thank for the organizers giving me a chance to speak in this session. I make maybe a full screen. So here we try to answer the question raised in past decades that what is the origin of the gamma ray burst Plateau phase. So we look for into the data to explain this. First, you are familiar this light curves, canonical light curve obtained from the XRT data. And I want to point out that this Plateau phase is affected by mostly with the flares. So flares needs very precise attention. And if we look at the data, canonical light curve obtained from the optical data, it is from the Tarot telescope archive. And you can see the Plateau phase here, but it might be also affected with other features like optical flash or reverse shock. So I want to say that we don't see all these features together. So you can see here the examples from the SIFT data. Here, the source that doesn't have the Plateau, and here the light curves that have a Plateau and with the flares as well. So the questions still remain, and we concentrated on 3 topics, like what can be the answer, like looking for weaving angle, late time energy injection, and the total density of the medium. So we find that the simple looks like is simple. The answer looks like simple. It took a while to arrive at. And there were some requirements, and one of the requirements that the Lorentz factor should be smaller than 100. We try to check this in the data, like when we compute from the thermal component, and there were 2 studies done on that point that we checked the non-dissipative photospheric emission with the data, and we didn't find any source that have a Plateau phase. And we also checked the one that we study that have a Plateau phase, if they are matching or if they are compatible. We find like one source, but the Plateau phase is really short, and the slope is quite steep. And we didn't find any evidence for thermal emission. And we also look at the LAT data, because you can use the opacity argument to compute the Lorentz factor. For example, in the second Fermi LAT catalog, there were 86 GRBs, but looks like the 3 of them show a shallow slope in the LAT data, but only one hard short burst show Plateau in the Swift XRT data. And however, the slope of the Plateau is still higher than what we consider in our work. And also the work done by the Yamazaki, and they look at that the shallow, either the source doesn't have a shallow slope, or the slopes are very larger than 0.7 in the X-ray data. So looks like the opacity argument is not valid for most of the Plateau phase GRBs. GRBs that has a Plateau phase. So another evidence that we see, we compare the source that has a Plateau phase and doesn't have the Plateau phase. And here you can see the black ones, the one that doesn't have, and the purple ones with the Plateau. And we didn't see very distinct parameter correlation in the closer relation. So we also checked the flux ratio, extrapolating the afterglow flux up to the bots. If there is a GBM, we include, and we saw that this ratio is varying. It's not like constant that can be expected from the energy injection. We also look at here in this data that looks like the GRB with the Plateau phase looks like more compatible with the wind more than the ISM. So the basic idea proposed by the Shen and Messer that the Plateau can potentially be explained by the steady flow into the wind medium, but the original idea applied only to the 2 years data. And they only use the X-ray data to constrain the physical parameters. Here in our analysis, we include the optical data with the careful analysis. We gave more freedom, fitting optical and X-ray data properly and removing any flares, optical bumps, optical flattening. And we also allow 2 breaks in the afterglow that end up with the steeper slope that can be after the jet break. And we identified properly the afterglow after the TA. So the underlying assumption was that the TA, which is the end of the Plateau phase, marked the transition from the coasting phase to the self-similar phase. So however, the answer that we didn't get from the data was lying in the observation that 1.5 thousand of GRB observed by the SIF satellites, only 1/3 of them known with the redshift. However, the 60% of this GRB show a Plateau phase. We also made more restriction in this Plateau phase, X-ray slope should be smaller than 0.5, maybe extend to 0.7. There is any feature of flares, even because in the Swift webpage, people, they identify this with the Wheeling function, but I think there is more to look at this with comparing with the theory. And we also required that there is a good data quality to perform the fit. So after that, we find that this was almost 60%. And we checked optical data, and the optical data is only 10%. And then when we divide this into 2 groups in X-ray, the X-ray slope, having X-ray slope like a flat or decaying. So this is just a cartoon. It is, for example, for this source, it's the flat Plateau is very suitable. And then the afterglow is proportional to the -1. So to apply this model was that we have to identify the TA, which is end of the Plateau phase, properly. And we need to identify the temporal index in the light curve, and we need to extract the flux in both bands. So doing that, we need to remove any flares. For example, for this source, looks like there is some feature of flares here. We need to remove that. Or for another source, there's a bump. If you fit like this and you end up more steeper, and then it will affect or the flattening. So these are the close look to the data. So when we make a fit, when we perform fit, you can obtain this increasing slope. But and then this slope, a second slope with the 2 breaks. The slopes looks like suitable, but what is the problem is the identification of the TA. The TA, for example, here in optical is earlier than the X-ray, if you should be earlier than X-ray, not like later. So then this create a problem. So if we remove this flare, that there is a flare, we also see in the flux density plot that it should be, and when we remove this, we get a compatible slope with the theory. And also another point that we look for, if there is bunch of data in the optical light curve with several bands, we put them together and fit them simultaneously. And if there is no data, we use the data from the Otis 2009, and we see the features, and we try to see if there is flattening or if there is like any feature, we try to adapt. This is just an example. It is this result like used for that source, but for the other sources, this is the careful analyzing and the source. So we also apply the for this analyze Bayesian method, and in the Bayesian method you can see you can get the errors in the posterior distribution. So this is also useful for determining the TA properly. So we put all these parameters into the closer relations to check the consistency with the Plateau and Afterglow. And you are familiar from the talk of Asaf pair that there is a region F and C, which is presented by this dotted line, and the region E presented with this red line, that this data is in the Plateau phase is very compatible, especially in X-ray. The optical, most of them are from archives, so it needs really the close look to the data. So, and here in Afterglow, it is the same case that the parameters are really suitable with the theoretical expectations. And we also can explain the larger Afterglow index being in the region E, which is the observed frequency is smaller than cooling frequency. So this is different than what Metzer and Shen and Metzer were struggling to explain. So here is our results. We put all these parameters into the theoretical model, and we here you can see the Lorentz factor versus the density, and we can deduce the data when we know that the X-ray is flat and the optical is decaying, and we can get the value of the gamma. It's in the order of like 5/10 between 20 and 200. And for the density, we can also get the upper lower limits if we know that both light curves are flat, or the X-ray is decaying and the optical is flat. We can give an upper limit. And to overcome the degeneracy, we use two assumptions that for the fraction of the energy of the magnetic field. And we find that the density is between like 10 to 3 to 0.1 for the one that we could deduce the results. And this is lower than the expected value from the World Trade Star. So here you can see the distribution of Lorentz factor. The average is 100. And so the initial Lorentz factor of the outflow is in the order of 5/10 rather than 500s. And this fill the gap between for the jetted outflow, the Lorentz factor that is expected from the jetted outflow, like from AGNs like Blazar cases, or from when you are using the opacity argument or the peak of the optical, that you can obtain the one that doesn't have the Plateau phase, you can obtain. And here you can see the sample that we studied fill this gap. So I would like to summarize all our findings. We know that the 60% of GRBs known with the redshift have a plateau phase. So end of the plateau phase marks the transition from the coasting to the self-similar expansion phase. And this outflow occur into the low density wind in the order of 2 to 3 order of magnitudes below the one expected from the Wolf-Rayet star. And we find that the initial Lorentz factor is in the order of 5/10 rather than 100s, and this fill the gaps between the agents and the one that obtained from the opacity arguments. And so we could manage to explain the plateau phase naturally in the frame of the classical variable model. And we don't need, in this case, energy injection or the off-axis observer or any addition by hand. So thank you.
Okay, thank you very much, Husna, for your very nice talks with many details. And I think we have time for one quick question or comment. If there are any, please raise your hand, or you can speak up directly if I don't see, the hands.
I got a question.
Up. Sure, Bruce.
Yeah, I'm studying a burst at the moment where basically I see the same thing than what you are doing, but the closure relations privilegiate an interstellar medium rather than a wind environment. Is your model really needing the wind environment, or it's something that could also be possible to be used inside the ESM?
So we study the wind environments, but some of the feature that in optical, I think, can also explain in the ISM, as also it is discussed in one part in the Shannon metal. If there is no break or early break is considered, but if there is no break, so yeah.
Okay. Thank you so much. And I think we must move on the next talk of the session. So let's introduce the next speaker, who will tell about Fan Xu, who will tell about the X-ray plateaus in gamma ray burst afterglows and their application in cosmology.
Okay, thank you. And first I want to thank Dr. Lee and Dr. Maria for organizing this wonderful session. And hello everyone, my name is Xu Fan, and I'm currently a PhD student in Nanjing University. And today I'm going to talk about my recent paper on X-ray plateaus in gamma ray burst afterglows and their cosmological application. You can check this paper with this archive number, and feel free to contact me with this email address if you have any questions or suggestions to our work. Okay, as the former speakers have mentioned, the X-ray plateaus describes shallow decay phase in the afterglow of the gamma ray burst. And here is a picture of a typical gamma ray burst with X-ray afterglows observed by Swift. The red curve is a fit of the
Sorry, we cannot hear you.
Okay, now I can hear. But we missed several of your presentation. I guess it was not only my problem. Can you hear me? Hello?
I can hear you, but I cannot hear the speaker.
Yes, I could hear the speaker for the first 2 or 3 slides. Fang Su, can you hear us? Okay, I think let's try to work it out this differently. So maybe if the speaker can contact the help desk for understanding what it is going on with this presentation, then we can meantime move on the next speaker of the session. So is it okay for you to do that like that, because no one can hear you? So we can move on to the next speaker, Dr. Mukesh Kumar Vyas, presenting backscattering dominating model for the prompt phase of GRBs to explain their key observational features.
Yes. Can you see my screen?
Yes, we can.
I'm happy to share my work. Thanks for the opportunity. So I'll be talking about the prompt phase of GRBs. We have carried out this work in a group with Asap Pierre at Byron University and led David Eichler. So I'll briefly present the background of the collapsar model and will outline what are the objectives of this work that we aim to explain. Then I'll describe the model and will present the results before concluding the talk. So when a massive star goes through collapse, like Wolf-Rayet star, it generates bipolar jets from the center of the star, which defies gravity, and then they escape to infinity to be observed by us. So what we see, a typical picture of GRBs is seen in form of a very common spectrum that is characterized by 3 parameters. The low energy spectral indices, roughly centered around -1, photon indices basically, and the high energy photon indices 1 order magnitude higher, and the peak energies in the redshift corrected spectra that center around 1 MeV or something. So these 3 features characterize the common picture of the spectrum that we see in the prompt phase from GRBs. So we pose the question, why do we have these ranges in all 3 cases, and then can we retrieve the overall picture of the bursts and their spectral features? Along with that, we also pose the question, why do we see this correlation among all the GRBs across the universe in all directions? We see very nice correlations that show that the burst may not be that chaotic. It has a very regular structure. So this is a correlation between the peak energies, spectral peak energies, and the total emitted isotopic energies. It goes like E peak is proportional to roughly the square root of E iso. So we'll be addressing this as well. Along with that, we also try to explain why the spectral lag exists, positive spectral lag, where the high energy emission comes first and the soft energies lag after that. So we try to club all these things together under a single umbrella of a physical picture. It's a bit different than what we have been talking about in this conference so far. So what is the idea? When a jet starts from the center of, the jet starts from the center of the star, material or the stellar envelope or the cocoon or cork, whatever you call it, is formed at the tip of it, which expands outside, and the radiation from behind impinges onto the stellar material or the cork. We call it simply cork. So we think that if this radiation does not penetrate the cork and is reflected backward, and the phenomenological argument can be given as if the cork is expanding with constant Lorentz factor, let's say 50, and if I inject 1 MeV photon in the cork frame, this photon will be roughly 10 keV. which is much smaller than the rest mass energy of the electron and is much, much smaller than the rest mass energy of the proton. So it may not be able to pierce through it, and most of the radiation can be reflected backwards. Reflection is not a proper word, it is actually scattered backward after having multiple scatterings inside. So we calculate these backscattered photons distribution in terms of its energy distribution as well as temporal distribution through a Monte Carlo simulation code. And what we see is, if an observer is along the is at an angle theta O at the with respect to the z-axis, then he will start getting the first photon from these edges of this black square S prime because of the relativistic effect. So this angle will be shaded because the backscattering radiation that's scattered in roughly the angle 1 over gamma will be shaded. So you start seeing the photons from here, and then the observer receives photons subsequently from different angles. So this overall gives him temporal as well as spectral evolution. So we try to see what will the observer see and what picture we get for the light curves as well as spectra, and do we see the picture that we observe? So to explore more about the geometry, if you look at the top view rather than this one, you will see that the observer initially does not observe anything from this region, then he starts observing the photons in form of circular wave fronts. At larger times, he observes it from distant angles, and we see that after certain distance, he starts seeing the arcs rather than circles. So it's not very difficult to find an analytic expression of how this photon count rate should evolve with time. And we obtain this expression here, which is written below. It looks a bit complicated. When we plot the light curves, we see that it is not that complicated. And the outcome is roughly like the photon should, and the light curve should decay by 1 by t square. So we plot here for various observing angles. These two angles are within the jet angle, which is 0.1 radian, and these two are for far axis observers. We can also predict what should be the peaks of these light curves for far axis observers. Okay, so then we move on to the spectral features. So initially in this project, we emit monoenergetic photons from the center of the star. And we retrieve these kinds of spectral features from a quark with temperature 10 to the 8 keV or roughly 10 to the 8 Kelvin or roughly 30 keV. So with this simplified assumption, we obtain some interesting features. For example, we obtain high energy power loss beta, which roughly comprises the values that are typically observed in gamma ray bursts from phase. And this high energy power law is actually arriving from the multiple scattering of photons inside the quark. When I plot the spectrum for different number of scatterings, L represents the number of scatterings, and then I overlap all of them, it produces the high energy power law, which is a simple textbook stuff. It can be found in ICRANet as well. And the photons go through multiple scattering in a hot medium, they are observed to be having the power law at the end. So this is good. But the problem that we have here is the low energy spectral slopes for the photon indices are positive, it's +1 here, which is not consistent with what we see. It didn't take, I will explain in later slides that this simplified picture also gives some other information. However, in spectrum, it has a problem with the low energy spectral slopes. It didn't take a long time for us to realize that it is coming because of the assumption of monoenergetic photons, which is not a very good assumption. It's just for simplicity. No source of monoenergetic photon exists in cosmos as long as I know. So we relaxed this assumption in the next paper, which is currently submitted. So what we did is we assumed rather than monoenergetic photons from the center of the star, we assumed a quantized pair annihilation spectrum, which we mentioned in the first paper as well, but we simply assumed the monoenergetic photons. So once we do that, we obtained low energy photon indices to be roughly -1, which is what we see. So now we have a typical picture of the observed GRBs similar to what we see. So we obtain both the spectral slopes as well as the peak energies, which is here roughly around 1 MeV. So we have this typical picture. So most of the GRBs centered around this alpha equals -1 and this beta equals roughly -2.4 or something. and the peak energies, which if you correct for redshifts, around 1 MeV. So this is a typical picture. But we see that for different observing angles, this peak energy shifts with respect to E peak is proportional to 1 over theta square roughly. This is just a relativistic impact. And if we change the temperature of the quark, we see that alpha and beta both evolve. So for hotter quark temperatures, you have a flatter spectrum, which is quite understandable. It will thermalize photons. It will produce harder spectrum at high energy ends. So we not only just obtain a single value of beta, but we have a variation as well across the various values of, let's say, from -1 to few at negative side.
Mukesh, if you can try to wrap up, because at 9:45 they will shut the connection. So,
all right. So this is
thank
typical
you.
distribution that we see in high energy photon indices, and the same distribution you obtain in low energy photon indices as well. The reason can be given to be the same. So if we try to explain the Achromatic correlation, it comes up naturally from the physical picture of the curved back surface of this. So we see that if I try to get various results for various Lorentz vectors and quark temperatures and various observing angles, and I map them, all of them in this distribution of E peak and E ISO here, we see that the nice correlation is obtained with the slope roughly 0.45. So this is what it is observed as well. And then we see at low energies or low luminous GRBs, there are some outliers, and we predict the outliers as well. The outliers are roughly coming because of the far off axis observers that start seeing the photons in terms of, that start getting the photons from arcs rather than full circles. So this is the reason for this outlier. So we explain that as well. Apart from that, if I talk about the positive spectral lag, the observer receives the first photons from here, and then he starts receiving the photons at different angles. So because of relativistic effects, it is well known that the E peak will go like 1 by theta square, or with time it is 1 by time, because theta is connected to time. So this is predicted, and this is what we typically see in various observations as well. Of course, this is not the overall picture. Sometimes it has a very complicated behavior, but roughly we predict this is what we should see, and this is what sometimes it is reported as well. So we phenomenologically explain this positive spectral lags and the Achromatic correlation along with the spectral indices. So this is how we conclude this. Our model does not include complex structure of magnetic fields and difficult photosphere and internal shocks and everything. But as a student of physics, it's